Hello, Physics 20. So I'm going to actually just do a couple of quick review questions here for you. Some of you are already comfortable with the Chapter 7 material, and this is just a little bit extra if you'd like to review. The test will be spread out over 2 days, Thursday and Friday. Anyway, I do want to hit, the answers are all here, but I want you to hit, or I want to hit a couple of questions here. I'm going to look at number 12. Classically, anytime you are given a pendulum, you can find a lot of information from that. So in this case, I have a 1 meter length pendulum, so that's L, and it tells me that I'm on a planet that has a mass of this. This would be M1, like the big mass, the mass of the planet. And it says it has a radius, the planet's radius is this number here, okay, 5.2 times 10 to the 6th. So if it wants the period, I want you to see how connected this is to math you've already done in the past. I know a lot of you have already seen this too. So the period for a pendulum is 2 pi times the square root of L over G. And in order to get the period, you have the length, but you don't have G. Okay? So the point is you can, in this case, you can find little g first. Little g is equal to big G times M1 over R squared. Okay, so your first step then is to do this calculation here using the mass and the radius of the planet. And then you take that little g and you put it right there. Okay, now it's really easy to go the other way. Like I could give you the period and and the length of the pendulum, and then say, if you know the mass of the planet, what's the radius of the planet or something like that. So the point is you would solve this guy for little g, and then you'd bring him over here and then carry on. So just know that those two are connected. I don't think you guys have any difficulty with that just as you see it, because it's really easy to use a pendulum to actually figure out some cool things about a planet. I mean, obviously it's all hypothetical, but just because little g is part of that relationship. Oh, and actually, yeah, here's 17 does the same thing. Look, this gives you the length of the pendulum L. Oops, sorry. Gives you the length of the pendulum L, and it tells you the radius of the planet, and it tells you the period of the pendulum. And then it says, what's the mass of the planet? You're like, what? Oh, well, if you know the period and you know the length, that's exactly what I was alluding to earlier. So we can manipulate this guy to solve for g. Okay, now remember carefully, you must square everything when you do that. So g and t squared are going to trade places. So I'm going to have 4 pi squared L over t squared, if I did that right. Okay, so there's little g. And I want the mass of the planet. So once I find little g, then I can dump him right there. And I can solve for M1 because I was given the radius R of the planet right there. Okay, so then I carefully manipulate that, and I guess I might as well finish that. M1 should be equal to little g times R squared over G. Yes, big G. Sorry, I'm trying to separate that from the other one. So yeah, there would be the mass. Okay, so yeah, using a pendulum, you can find all kinds of stuff. Yeah, don't forget this either. I know I did read, there is a video, a short video I tried to post on resonant frequency, forced frequency, and mechanical resonance. For sure, you should be able to define those, like know the difference between all three of them, be able to give me an example. You can use the examples I shared or come up with one on your own, it doesn't matter. But I want you to know those. You'll see why when we get into studying waves, there's a huge correlation between what we're learning right now in Chapter 7 and the physics of waves and understanding wave anatomy. So that's why I want you to understand that theory. This last question here can be a little bit tricky, but again, I don't think it's horrible once you've seen the setup. We have a ball that's initially not compressing either spring. I'm actually going to color code these a little bit. So we're going to take the center spring, we're going to make that red. Okay, so in the initial position, both the skinny spring and the fat one are not compressed. And then in the second position, both the skinny spring and the I guess the bigger, the wider one, and we're going to call that the blue one. Okay, so maybe we just call them red and blue because now I can color code them. Okay, so you have the red and the blue spring. In the second position, it says the ball is in equilibrium. Okay, so that means that the ball is at rest. That is a really huge clue for this question because I haven't even gotten into any numbers yet, but what it's really saying is if it's at rest, then it means that all the forces on it are balanced. So that means there's going to be gravity's trying to pull it down. But what you need to see is that the red spring doesn't like that you've squished it. And so it has a restoring force up. The red spring wants to go back to equilibrium, but guess what? So does the blue spring. Okay. So you have two restoring forces up. You've got two springs that are pushing up, and gravity is the only force down. So the big picture, which some of you are maybe seeing now, the big picture is that the force of gravity down is going to equal the restoring force of, it doesn't matter which one you do first. Maybe we could call this the restoring force from spring number one, or the red spring, plus the restoring force from the blue spring. Okay. Now, what that's going to turn into, though, is really this. Okay. For the restoring force on spring number one, that's going to equal, technically it should be a negative kx1. Okay. Or actually k1x1. Okay. So we're going to say that the red spring, it has its own k constant. In fact, it's listed here in the question. There it is right there. That's the longer spring. Okay. And we're also going to have a negative k2x2. Okay, sorry, I ran out of space there. So we have the restoring force from spring number one and the restoring force from spring number two. What you have to be careful of course, is getting the right k values first. So I think we got the red one okay. Right, the shorter spring. What is the spring constant? We don't know what that one is. So in this case, that's my unknown. Okay. The force of gravity, of course, is m times g. So you see here, I'm just kind of playing this out. So what you have to account for, which you don't rush into this because I'm giving you extra detail to force you to slow down. Let's look at just the red spring. The red spring is initially at 35 centimeters. That's height number one. And the blue spring looks like it was initially at 25. Okay, the shorter spring had an initial length of 25 centimeters. Okay, but it's squished down to height number 3. Okay, height number 3, well, I guess we'll just do that. Height number 3 is 20. Okay, so the red spring, and this is what you have to catch, the red spring went from 35 to 20, and the blue spring only went from 25 to 20. So when you're calculating x in both cases, like I'll maybe say, let's do red first, x1, that's going to equal 0.35 meters minus 0.2 meters. Okay. X1 went from 0.35 down to 0.2. Again, I converted that into meters. That's an easy mistake too, if you missed that. And then X2 will be the 0.25 meters minus 0.2. Okay, so that's the change in X for the fat spring or the blue spring. Okay, so as long as you're keeping track of those, you get those two numbers correct. X2 obviously will go up here, and X1 will move up here. And you know the K value for the red spring. We already have that. And you know M and G, of course, because this is on Earth. So you carefully manipulate and solve for K. Now, here's the one thing too that's a little bit technical. If you just see that the force of gravity is down and that these two forces are up, okay, you can kind of trip over the negatives here because it's negative kx. Technically, x, though, would be a negative, so that would make it a positive. If you miss that, then you're kind of getting your negatives and positives all confused. If it helps you, just drop the negative from the formula and recognize that the forces are going to be up. The restoring forces on both springs are going to be up, and the force of gravity is going to be down. Okay, so whatever, and that they have to equal each other, because in this state of equilibrium, the amount going up has to equal the amount going down. And so really, if you want, you can just kind of ignore all the positives and negatives, if you maybe you're seeing that now, because you just need this total amount on the right to equal the total amount on the left. Okay. And anyway, there's a couple of ways you could address that, but I'll make that tip if that helps you. And I'm hoping that will help you in this case solve for K. So anyway, you can ask me more questions if you have on these. These are really similar to the review questions you've already done. So, I mean, you might get into them and go, I'm fine, I don't really need to do them all. But if you want the extra practice, you can. The test that I'll open tomorrow and Friday is only on Chapter 7. I haven't even looked at it yet. I think it's like maybe 13 or 14 questions. And you can complete that online. So anyway, let me know if you have any questions. We keep up the good work, you guys.